I'd like to look at how we can calculate area under a curve when that curve's defined parametrically. So I want to start with a little reminder of area in the Cartesian realm, the way we looked at it previously. So recall that if you want this area under the curve above the x-axis from some x equal a to x equal b, previously we saw that area can be the integral from a to b of y, or f of x, with respect to x. Now, there's a couple things hidden here in this picture that I haven't explicitly said. Let's think about where this came from. The Riemann sum was a bunch of rectangles, right? And we found the area of those rectangles and let the norm of the partition go to 0. But what was key, for that to really be area, truly area, this has to be giving us the area of those rectangles. And so first of all, the function, there was two criteria here. Y needed to be greater than or equal to 0. That guaranteed that all of our rectangles actually had a positive height, right? Once this curve here dips below the x-axis, then the integral is no longer area, because then the rectangles below would start to take away area, and then you're not really getting the area between the curve and the axis. So the function had to be greater than or equal to 0, so your heights were positive. The second thing we didn't even really think about all that much because we just became habit was this number was always smaller than this one. Now it seemed kind of trivial, and we'll just say less than or equal. What does that guarantee? Well, in the way we define this, x is going from this point to this point. So in your little rectangles, so let's think about this. Let's just draw one. One of your rectangles is going to have some height, y, and some base, delta x. But in order for the base, we probably didn't give much thought to this in Calc 1, but that base needs to be positive too. You have to be going from a smaller x to a larger x so that all your changes in x as you move from that point to that point, all your changes in x are positive. That's precisely why when we learned that rule in Calc 1 about how when you switch those limits, you get the opposite integral. It's because your changes in x now are all going this way. Your heights are still the same, but the bases of all your rectangles are the opposite of what they used to be. So the reason we never gave this much thought is because we always just kind of got in the habit of you put the small number down here and the big number up there. But we're going to have to be a little bit careful when it comes to parametrically defined functions. So let's think about this. I'm going to label these so we're clear. These are x's, right? That's the Cartesian way. But what if our curve was defined parametrically? So let's say x is f of t, and y is some g of t. And I'll even, just to avoid any confusion, we'll just call this curve y. I don't want to call it f of x because I don't want you to confuse that f with this f. Totally different thing. So, but we can replace these quantities with these, right? Y is, in a parametric, is defined as g of t. And dx is differential, right? So remember, from our definition of differential, dx is df dt dt. So all I have to do is swap this out in place of dx and this out in place of y, and I've got area for a parametric. Now, what about, I'm going to call the starting value some t sub a and the ending value some t sub b, just to remind myself that that's the t when I'm right here, and the other one is the t when I'm right here. Right? Y is just g of t, and dx is derivative of f with respect to t dt. So we can simply just convert that equation over from a Cartesian form to a parametric form. Now, here's where we have to be careful. this t is not necessarily smaller than this t. Imagine our direction of motion is this way, from t sub b to t sub a. What's key is that this needs to be the smaller corresponding x, and this needs to be the larger one. So these t's could, ta could be smaller or bigger than tb. What needs to be important is you need to make these limits so that the direction of motion as you go from that t to that t is from left to right, or increasing x, because you still want your delta x's to be positive. And we'll do an example where we have to be careful of that so you can see what I mean. But we want this to be where we are farther to the left and this one to be to the right, so that our motion is in increasing x, whatever those t values might happen to be. All right, so let's look at an example here. Let's do the ellipse. Let's do an ellipse here. Let's find the area inside let's say 3 cosine t, 2 sine t. So we've looked at ellipses. Remember, this is a circle if it's just cosine and sine, but we've stretched by a factor of 3 in the x and 2 in the y. So more stretch in the x than in the y. Cosine runs from -1 to 1, but when you multiply it by 3, it runs from -3 to 3. So our x's go from -3 to 3. Sine goes from -1 to 1, but now times 2, it goes from -2 up to 2. So there's our picture of our ellipse. Something like that. OK, now I need to set up an integral, keeping these two things in mind. Y needs to be positive, and I need to be going in an increasing x direction. Well, we could keep y equal positive by taking advantage of symmetry, right? We could just do the area underneath the top half and multiply it by 2. So what's the top half? Well, when t equals 0, you're right here, right? X equals 3, y equals 0. So here we are at time 0. And then we move around. This is the counterclockwise until we get over here to t equal pi. So this is exactly what I don't want, right? I don't want to go from t equals 0 to t equal pi because my x's are getting smaller. This would be a negative quantity. So I'm going to go actually from pi to 0. I'm going to go backwards in time, but forwards in x's. So my area is going to go from pi to 0, so that I go in the increasing x direction. And I want to just do the top half. Whoops, I should have left myself some room. I'll put it right here. It's going to be twice. Because of symmetry, we're just doing the top half, so I have to double it. Y dx. I usually don't remember this. I don't think of it that way. I just think of y and the differential dx. So y is 2 sine. And dx, take the differential there, is -3 sine dt. And there's our integral. So we've guaranteed that we're going in an increasing x by going from pi to 0. We were opposite the parameterization direction there. And we only did the top half, so our y's are all positive. And we doubled it because of symmetry there. OK, so we've got what? 2 times 2 is 4 times 3 is 12. So we have -12. The integral from pi to 0 of sine squared. And remember, from way back at the beginning of the semester, we use our trig identity on that. So it's 1/2, so -12/2. The integral from pi up to 0 sine squared is 1/2 1 minus cosine 2t. And then now we can integrate. So that's -6. The integral is t minus 1/2 sine 2t from pi up to 0. 0 into there is 0 minus 0. So we have -6 times 0 minus 0. And what about at pi? We'd have minus pi into there is pi. Pi into there is 0. So we have just -6 times negative pi, or 6 pi. I'll put this up here where you can see it. All right, so it's really just the same formula. I wouldn't bother memorizing anything new. You know that to get the area, it's the function dx, the height, the width. And then just think in your definition, what is y? What is the differential dx? And just be careful about your order. You want to be going increasing x's.